draw anymore because function f now three-dimensional space, and then ds now a curve on the three-dimensional space. Okay, and then what? ds very similar to the one before, but now you got one more variable, so square root of what? dx over dt square plus dy over dt square plus dz over dt square dt. Okay? And then you think of x as a function of t, y as a function of t, and then z as a function of t, and you have the integral in one variable. Integral from t0 to t1 f of xt, yt, and then zt, and then square root of dx over dt square, dy over dt square, dz over dt square, dt. And again, I cannot draw it out anymore, but very similar to two-dimensional line integral that you had before. Just add one more variable. Okay? And the technique to solve this problem is what? You try to parameterize this. Try to find out the function x in terms of t, y in terms of t, z in terms of t, and dx is dx of dt, dy, dt, dz, dt square root, and then dt. And you integrate it, so you have the answer. Okay? There is one very special case, one very useful techniques that you guys should know when you deal with straight line. Use vector then. Say x-axis right here, y-axis right here, z-axis right here. What if your C, the curve C right here, is just a straight line on the xy plane from the point, say 1, 2, 1, and to the point 1, 3, 7, for example. Okay. So how do you parameterize this? How do you find the equation of the line segment? Actually, you guys did that before. I think it's way in chapter 12. But let me just try to recall using vector. Vector r of x, y, two variables, right? Equal to what? 1 minus t vector r naught plus t times vector r1. Okay? R naught is the initial point, and r1 is the final point. And t is now your variable parameterization variable. Okay, so what is R naught? If you go from the first point to the second point, go this way, then R naught is this, and R1 is this. Okay. Oh, it's in 2D, so XY plane, so I should not have Z in here. Take it back. Okay. 1, 2 to 1, 5, for example. And what? This is R XY is equal to 1 minus T. So Rxy can be written out this way. X comma y, right? Yeah. And 1 minus T, and R1 is 1 comma 2. Angle plus T times 1 comma 5. Okay. So in here it's being what? X is equal to 1 minus T times 1 plus T times 1. Okay. T times 1 plus T. Good. And then y here is 1 minus t times 2 plus 5t. 1 minus t times 2 plus t times 5. Now you have function of x in terms of t, of course simplified. You have function of y in terms of t. You have the parameterization of the line segment from 1, 2 to 1, 5. And if you have the line go backward from 1, 5 to 1, 2, then this is going to be 1, 5, it's going to be 1, 2. We talk about that in what? If this is a curve C, right, from 1, 2 to 1, 5, then if you want to integrate from 1, 5 to 1, 2 backward, and people usually write this way, C with a minus sign in front. Means what? The same curve, you just go the other direction. And guess what? The answer is going to be the opposite of whatever you have for the original one. Okay. So, integral of negative C f ds is going to be the same thing as integral of f ds with the minus sign. This means what? The integral of the function f ds with the curve C going from B to A. And then this is integral still f ds, C from A to B. And then you whatever the answer you have, you put a minus. Okay, that's what it is. Just like when you do count 1 integral. Integral from a to b, f is equal to negative integral from b to a, f. You go from a to b, you go from b to a, backward. You have the opposite answer. Okay? Let me see if I missed anything in here. Oh, yeah. Now let me talk about the line integrals of vector fields. Line integrals of vector field. Okay. So instead of talking a function ds, now we're looking at it this way. The integral along the curve C of a vector field f times dr. Okay. Dr is change of the vector r direction. Okay. So there's a lot of application in here. Let me just try to explain it to you and demonstrate it using a little bit of physics. Okay? This could be applied to anything. Think of f right here is like force. Okay? This is like distance. Okay? And this is dot product of two vectors, distance. Okay? So in physics, what happens if you take the force times the distance? You have something called the force, right? So if this is my curve C, run from the initial point right here from A to B, say for example, and say you have an object, you put it right here, okay, and you're going to use some force to push that object along the curve C to get to the point B. So every time you change the distance a little bit, you have dr, right? And then you time the force, you're going to have what? A little bit of the work, of the energy that you put in here to move it a little bit. And then you add all the little work that you have, add all little work you have. This is the total work that you need to move the object from the point A to point B. And this is what it is. Okay? Think of it as like energy, the work right here. Force times distance. Okay? And you see what we have to use integral because what? The force may not be a consistent, may not be a constant, right? The force you apply this moment right here may not be the same as the force when you use right here. Okay? Vector field, force changing. Oh, that's why we use integral. If it's constant, then all you have to do is what? F times the distance, and you have the length of that curve, and you have the answer. Okay? Okay. And how does it apply to how to translate formula into a math equation to work, right? If you think of f, vector field, we call this what? X, Y, Z. Let me do X, Y, the same thing as X, Y, Z as we went before. Okay? Two variables. Then what? This is the vector field on two-dimensional space. And then the vector R is the equation of the curve. Okay? The curve C can be represented as the vector R. X, Y. Okay? Now, we can, one way of solving this problem is, again, parameterize everything. So think of f as f of xt, yt, right? We write the position x, that's the function x until t, and y is the function until t, right? So r right here, you can write what? rt, xt, yt, okay? So this is going to be the vector function representing curve C, okay? So what is dr now? Dr, let me see how the book write it. Dr is, remember we have this before, this now is a couple of ways to think of it, right? Let's see. Dr now is what? R prime t and then dt, derivative. I think we learned it in chapter 12, I think, or chapter 13, around there. So dr, let's think of it as what? R prime t times dt, okay? And f is what? This one is f of RT. Okay? So this becomes what? Integral f of RT times dot product of r prime t and then dt. So you have this one until t, right? You have the r prime t, you dot product, and then time dt, and t run from say t0 to t1, and you have the integral to calculate. Let me go back to the previous example that we've done before. Let's just make up one. How about fxy is equal to, what did I give you before? I think it's what, let's just make up one. 2x plus y comma y minus x, for example. Okay? And then the line C right here is what? Y equal to x squared, right? Okay. And right here. And run from 0, 0 to 1, 1. That's what we have before. And this is 0, 0 right here, 1, 1 right here. And this is the curve C that you're talking about. Okay. So apply it to the vector integral, line integral vector. As usual, like x equal to t. Well, it depends on problem. This is just one of the simplest way, okay, to parameterize. And y equal to x squared, so t squared, right? And r t is gonna be what? xy, which is t comma t squared. Okay, this is x. This is y. Okay, so r prime t is gonna be 1 comma 2t. You see what I've done? Derivative, derivative. Okay, and my f is what? F xy becomes 2x plus y is gonna be 2x is 2t plus t squared, and then y minus x is t squared, it's y squared, y, right, t squared minus t. Okay, now you dot. Take f right here and dot the r prime. Okay, so f of xy dot r prime t is gonna be 2t plus t squared comma t squared minus t, and then you dot 1 minus 2t. And remember how we dot two vectors? First term times the first term is comma. Okay. First term times the first term, the second term times the second term, and add them up. I'm running out of space, right? So I'm going to write on the left hand side. It's going to be 2t plus t squared plus t squared minus t times 2t. T squared minus t times 2t, and this is variable term of t, right? 2t plus t squared plus 2t cubed minus 2t squared. So this is going to be 2t cubed minus t squared plus 2t. Okay, so this one becomes the line integral of f dot r prime t dt. And this is going to be f dot r prime, we calculate right here. It's going to be integral 2t cubed minus t squared plus 2t dt, and t run from 0 to 1, and x run from 0 to 1. The t equals to f, and you can integrate that. That was the idea. Again, looks more work, but not too hard. Okay? So the main thing that I tried to bring to you is this. F, line integral of the vector field f, time dr, change of distance, can be parameterized into variable t and run from t0 to t1, whatever it is, okay, for a change of t. And dr right here is r prime dt, and f is now becomes a function of t. And what you're going to do is what? You dot product in here. You're going to have a function that's of t, and you integrate. Okay? We can derive one more from this. We call that the tangent vector is r prime over the magnitude of r prime. Is that right? We learned this before. Okay, so this is what? Integral of vector f dot, if you write this way, r prime, okay, so over r prime magnitude, of course t, but it's long, so let me just write that way. And then you time magnitude of r prime, and then dt. It's going to be the same, right? I divide by the magnitude of the tangent vector. This is called the unit tangent vector, by the way. And you multiply back, it's the same. Okay? So this is what? Integral of f dot, this is the tangent vector, and you know what? This is really ds. You see why this is ds? S, remember, ds is what? Square root of dx over dt square plus dy over dt square dt, right? Where r t is what? Dx over dt comma dy over dt, right? And then the magnitude of vector r is going to be dx over dt square dy over dt square, which is this one right here. That's why we have this way. And I show you this with diagram most of the time. This is the key. It's the one they use to solve for line integral of vector fields. Okay, let me show you another way of thinking of this problem. If you don't want to parameterize it in terms of x, y, z, you can integrate with the integral respect to x, y, and z as we've seen before. Another way, okay? So let me erase this. Recall that f is a vector field, okay? F can be represented as what? P comma Q in two-dimensional space, where P is a function of x, y, Q is another function of x, y. And R is x comma y. Okay, it's just the curve, right? This is the curve C, represented as a vector, x, y. So f dot dr, so dr you can think of as dx comma dy. Okay, now you dot this. This is what? PQ dot dr, I'm sorry, dx dy integral, dot product right here, you got what? Integral of P dx plus Q dy. Okay, this is the integral. I'm going to put another integral right here. So this is the right way to write, and then people getting lazy, so they combine the two integrals as one to write this way. Okay, but technically it should be this. Means what? Function P right here, now it's normal vector, right? P here, this is f x y, this P x y right here, and then Q x y. Those are functions. This is a vector field function, right? Function of vectors. Okay, f x y is P x y, Q x y. Then you can integrate that line integral over the vector field f on the curve C, represented by the vector r right here. You do what? P dx. Okay, P is the first component of vector f times dx, and then Q dy. And similarly, if vector f right here in 3D is what? P Q R, then r going to be x y z. Then you have what? P dx, Q dy, and what? R dz. You integrate 3 times 3 integrals. First component, second component, and third component, you add them up. You have the line integral of that vector field, that's why. So this is another way to take care of the problem. But it doesn't matter what, if you go here, and I claim that eventually you're going to do parameterize anyway. Remember I showed you what x in terms of t, right? And p right here, goes to xy, convert it to t as well, parameterize it, and then same thing for dy, same thing for dz. Either way, usually people parameterize it in terms of t, and then they integrate it using count 1. Okay? Let me see if I missed anything. Let me graph up this video clip today by giving you another example, okay, of a line integral over the vector. I give you an example already. Give you another one. This one's coming from the book. Okay, so they ask you to find the work done by the force moving a particle along the quarter of a circle. All right, so they give you a vector field. Force F, x comma y, equal to, see what I got in here, x squared and negative xy. X squared and negative xy. Okay, so this is really my p function, pxy. Okay, and this is my q function, xy. Okay. And then this is the quarter of a circle, represented by vector r. T, use T, right? Let me make sure that I use the same. Yeah, is what? Cosine T, comma, sine T. Yeah. So really, this is your x right here, and this is a y value point when T changes, right? And they give you the boundary for T. 0 less than or equal to T less than or equal to pi over 2. Run from T equal to 0 to T equal to pi over 2. Okay? And the force, you know the force times the distance is going to be your work, right? So work can be calculated as the sum of all the little work that you have. Okay? And the little work is calculated by what? The force times the little distance that you move. You add all the force times the little distance that you move, you have the work. Okay? And this is your F right here. This is your equation for the curve C. So x is cosine t. So x squared cosine squared, right? And this is what? Cosine times sine t. Okay? So force F is what? Cosine squared t, comma, negative cosine t times sine t. You know, this is really x squared, and this is what? Negative x times y. Okay? And r prime t, this is rt, r prime is the derivative cosine is negative sine t, and the derivative sine is cosine t. Okay? So f dot r prime, I'm getting lazy at writing t, so you know what I mean, right? This is what? Cosine squared times negative sine t, so negative sine t cosine squared t, and this is what? Negative sine t cosine squared t. Was that right? Yeah. Which is, it's the same, right? So negative 2 times sine t cosine squared t. So this integral becomes what? Integral t run from 0 to pi over 2, 0 to pi over 2. F dot dr is f dot r prime dt. So you have this. So what? Negative, I'm going to put the negative outside. Negative 2 outside. Sine t cosine squared t dt. And you know how to integrate it. Let u equal to cosine t. Then du is negative sine t dt. You have the answer. Okay? And that should be the end of our clip today. Cover section 16.1 and 16.2. So on 16.1, we give you the introduction to what's so-called the vector field, and we have something very special called conservative vector field. If that vector function right here is a gradient of some functions, okay? And on 16.2, which is the main one, I think, is about line integral. We integrate a function above a line or curve, okay? And we have line integral over a vector field. Let's show it here. And if this the first time you deal with force, I'm talking physics in here, the first time you deal with force or distance or work in here is a little bit harder than for those who's physics before. So I'm not sure that I know a lot about physics, but you all feel free, more than welcome to ask questions. Okay, I'll try my best to explain everything I know to you. Again, just ask, and we have a chance to talk, and we have a chance to figure it out. I'll I'll stop the video clip right here. Thank you for watching, guys, and have a good day. Bye-bye.